Alright, so I've been fiddling around with my concept of the sub operation within taking limits, where you get to the closest possible value to the value you're taking the limit of. And in this case, the value that I'm looking at is 0, so L of 0, or L naught, is the closest possible value to 0, which makes it the true successor to 0. And this is the source of the paradoxes which arise when 1 is considered the successor of 0, because L naught has no scale relative to 1. 1 defines the scaling and can be placed anywhere along a dimension. But since 1 defines the scaling and L naught is defined relative only to 0, there is no set relationship between L naught and 1. This results in L naught behaving unexpectedly with mathematical operators because it has no unit. So we get interesting things. Some of them are not all that weird, but some of them are weird, right? So here, L naught plus L naught is L naught, or L of L naught. So that operation applied to itself applied to 0, which is the same as 2 times the value of L naught, right? Because the increment between the successors is identical, so the limit of 0 is 2 steps away from 0, because we did it twice. Which means that n times L naught is the same as taking the limit n times of 0, where n is an integer, because we cannot take fractional steps here. We can only take whole. You can only apply this operation or not apply it. There's no in between here. 1 on L naught will be infinity because L naught is infinitesimal, right? So what this is, this right here, 1 on L naught equaling infinity, is when you take the limit as x approaches 0 of 1 on x. That limit evaluates to infinity, right? As x approaches 0, right, x ideally gets all the way to L naught. And when we evaluate 1 on L naught, you get infinity. So that is necessarily true. Now this is 1 on L2 naught is 1 on 2 times L naught, which is less than infinity, but only just. It's just 1 step away from infinity. Or another way to put that, more than 1 infinitesimal is no longer infinitesimal. Or another way to put that is, if we added the infinitesimal L naught to 1 on L2 naught, then we get 1 on L naught, which is infinite, right? So while this itself is less than infinite, so it's finite, if we just added that infinitesimally small, the smallest possible thing that you could ever add, if we just added that much to this value, we would reach infinity. And then you can generalize from this. So LA naught, that should be a naught right there. LA naught. Wow. Keyboard's at a weird angle to my hand. Okay. LA naught plus 1 on LB naught is 1 on LB minus A naught, where A and B are integers, right? So because of what all is happening here, this addition here becomes a subtraction in this denominator term right there. And then conversely, when we get a subtraction here, we'll get an addition in the denominator. So 1 on L naught, which is infinite, minus L naught is 1 on L2 naught, or finite. So this infinity right here is the smallest possible infinity, because you can actually break out of it by doing a very special thing. If you subtracted a unit from it, it wouldn't become finite. But if you subtract this very specific thing from it, then it becomes finite. And that is a consequence of this, that there is no scaling between these two things. Right? There's no relationship between these two things. So that is not a contradiction. That is not a paradox. That is something that we should be expecting. Yeah, because we're working with this, not units, not integers or reals or something like that. It's a completely different class of thing. Yeah, and then just like above. So when we subtract that thing off, if we apply this however many times, and apply this however many times, then we'll get this. So that subtraction becomes an addition in the denominator. And then this guy, if we take 1 on L naught, that quantity, and divide it by some integer, specifically a non-zero integer, then we get 1 on n times L naught, or 1 on ln naught, which is going to be less than infinity. So we can take this infinity and we can turn it into a finite value by either subtracting or dividing it, as long as we're working within the terms of L naught. So this is a special sort of thing, and there's some indeterminate forms here. I was just looking at indeterminate limits and stuff. But note this part up here, where we started, right? If L naught is the true successor to 0, then we can look at what Peano was trying to do. So if 1 refers to L naught, then some nice things happen. Multiplication works normally. This kind of gets a little bit messy. Okay, so we already saw this, right? So since ln naught equals n times L naught, and L naught is 1, because we just defined it that way, then this whole thing is just n times 1, or it's n. And this is an unfortunately circular, or perhaps just incomplete. I think it's really just incomplete. I don't really have the motivation or the space right here to put in a complete definition, anyway, of the numbers. And since numbers are required for addition and subtraction, we must define them here first, right? So there is a way, I'm pretty sure, to make this not circular, but as it is, you can see that it is, because we're yielding a definition for a number, but we're using that number in the first place in its own definition. So this is circular. It's not properly defining them, but you can kind of see that down here we're using multiplication, so we have to define multiplication first. We have to define how the multiplication works first before we can get addition and subtraction. But then down here, you get addition works normally and subtraction works normally, right? So LA naught plus LB naught is A times L naught plus B times L naught, which is the same as A times 1 plus B times 1, which is the same as A plus B. And the same with subtraction. But division's a little bit of a bastard, right? Because we have by definition that 1 on L naught is infinite, but also 1 on 1 is 1. So we end up with this problem. What does this mean? What's going on here? Well, what's going on here is that L naught is indivisible. Thus 1 is similarly indivisible, rendering any division with 1 in the numerator nonsensical. So, yeah, that's where that's coming from. It actually, when you think it through fully, it does make sense that we're having a problem here, right? It's unfamiliar, it's an unfamiliar problem, but it makes sense that it's there. But then if we look at something like L6 naught on L3 naught, we'll get 6 by L naught on 3 by L naught, and that is the same as 6 by 1 on 3 by 1, which is 6 on 3, which is 2. That works out nicely, so sometimes division can work. But if we're using coprimes, we're going to get nonsense. So like L8 naught on L3 naught will turn into 8 on 3, which is larger than L naught. It's larger than our unit, 1, but not a multiple of L naught, and thus it's infinite, because the count cannot be completed, because we can only count by L naught units, right? So if it's not a multiple of L naught, then we have a problem. We can't finish the count, which is what infinite means. It means you cannot finish counting it. So technically it is infinite, because we cannot finish the count. We cannot get to the end of it. Thus, if 1 refers to L naught, we must be working with integers. Now, importing the division rules for L naught, we get these. So this we just saw. 1 is indivisible within the integers, so this is uncountable nonsense. That's why this 1 on L naught is infinite. Basically what I just said. Right? And again, here we get 1 on something. This is uncountably small since the count cannot begin, resulting in the value being less than infinite, but still uncountable. Right? So it's here, this, what I mean here is, the huge infinity that you normally think of. Right? Right? It's less than 1. This thing is going to be less than 1, but you still can't count to it. It's not an infinitesimal. It's just some fraction, but fractions are not integers. We can't deal with fractions here. And then this guy, so it's uncountably small value, and again an uncountably small value, and again an uncountably small value. So these weird things that came up with the divisions that were yielding infinities and things that are just almost infinities, they actually do still tell us things correctly when we use L naught as our unit, and that means that we're working within the integers. So I thought that was interesting, because it more or less seems to work with a traditional sense of integers, but there is a little bit of added. I'm split between calling it baggage or calling it clarity, because it's explaining, in a way, what is going wrong with things like 8/3 or 1/9 with respect to the integers. So I'm not sure which it is. I'm not sure if it's baggage or clarity, but it's somewhere in that vicinity, in that ballpark.